What's special about this here, in this example here, is that it says that until he was in his seven, Henry Lamotte excited audiences by belly flopping from a height of 12 meters into 30 centimeters of water. Well, that's pretty impressive. Uh, dude, that's like 36 feet up into a little tiny pool. That is impressive. And it turns out that Harry Lamotte is a very odd guy. It turns out that he was a medical doctor in France, and he says that when he was in med school, he lost a lot of his friends because he had to study so much. So his hobby became belly flopping in the pool in the apartment complex that he lived at. So he continued this even though he finished med school. And assuming that he stops just as he reaches the bottom of the water and estimating his mass, draw an impulse momentum bar diagram and find the magnitude of the impulse on him from the water. Well, let's look at a picture here. So my pictures is going to look something like this here. So I imagine that I have some high dive, right? Right? Here's my high dive right here. And down here, what we're going to do here is that we're going to put in a little pool of water, right? And what Henry's going to do, right? He's going to be standing right here. As far as I'm concerned, he's like a superhero for actually wanting to do this. And then apparently he's going to do a belly flop into this thing, right? I don't know how you do a belly flop into something like this, but I could imagine that he's probably doing like this, and you could imagine his arms are sort of like up like that. And of course, because he's going to do something that I would never do in my life, he's like Superman to me, right? He's got his cape on. And there he goes. So what we're most interested in is that we can see here is that the height that he's falling from is, of course, 12 meters. And then this height right here is 0.3 meters, right? Which is a tiny, tiny amount. And so what we're really looking at here, if I think about the impulse momentum theorem, what I'm thinking is this. So from the impulse I'm always thinking P1 plus J equals P2. So, but let's think about this thing here. So when I think about P1, what am I thinking about in terms of P1? What I'm thinking about in terms of P1, it's going to be his speed or its momentum right before he hits the water, right? So this guy's going to be his momentum just before impact. And then this guy right here has to be his momentum just before hitting the bottom. And so if it's what we're hoping here is that that 30 centimeters really does what? We're hoping that the momentum of this guy should be zero, right? It should be zero. Because if he hits it too hard, obviously he's going to get hurt. So then my picture-wise, I'm imagining here is that here I go. So then my bar diagram tells me this. I got to pick a direction now. So I always almost always pick my negative direction to be the direction of the initial momentum, and then my positive to be in the opposite direction of that. So in this case, what is changing the momentum of Henry? It's the impulse of the water, right? It's the impulse of the water. So in this case, what I'm seeing here, if this is how much momentum Henry has, and we'll say that it's going in this direction, so this would be his initial momentum, then the impulse should be in the opposite direction, which is positive in this case. And of course, it's in the opposite direction. So then here's the impulse of the water. And so if they are truly equal and opposite, then afterwards, the momentum of Henry should be exactly zero. So then I'm going to go through my bar diagram. What does my bar diagram tell me? Well, look at my momentum. It's negative. So I get minus P1 plus J of the water must be zero, which then tells me that the magnitude of the impulse should be P1. That's what the impulse momentum theorem is telling us right here. Okay, so that being said here, to get the water, we need to get the momentum at that one point. Remember, this looks like I'm only looking at one point. Remember, this is a change. Why is this a change? Because look what happens. When I look at really the impulse of the water, it's really 0 minus P1. There is a difference right here. I'm not talking about a momentum at one point. I'm talking about 2 points. So if I look at this, then to get the impulse of the water, we write that J of the water, that means the magnitude, we already know the directions is, of course, mv1, and from this here, we have to calculate the mass and v1. So let's do this here. So what about the mass? So if I go back to our problem right here, you could see here is that the first thing that I got to do here is it says estimate his mass. What's his mass? I don't know. If you Google the average weight of a man is about 70 kilograms, there it is. So our estimate for the mass. So then here, what we're going to do here is that we're going to do this here. We're going to estimate mass. So we're going to say mass is about 70 kilograms. And so then V, we have to calculate. There's lots of ways that you can calculate this thing. Probably the easiest way to do this here is to use conservation of energy. So that's what I'll use here. So from conservation of energy, we could see here that there's a certain amount of potential. So if I look at this thing, I have this amount of gravitational potential to start off with, right? And then right before he hits the ground, he's going to have this amount of kinetic energy 1. So if I look at these guys, what I'm going to do then is, of course, I'm just going to solve this simple equation here, which then tells me here that mgy initial must be 1/2 mv1 squared. So therefore, when I look at my mass terms, they cancel. And so this tells me that v1 must be 2gy initial. So I now know what the speed is here. So now if I then substitute this into our impulse, it's got to be mass times the speed, which will be 2g y initial. And if I plug in my values, I'm going to say that this force should be 70 kilograms times the square root of 2 times 9.81. The height they tell us is 12 meters. And then if I compute this value, I end up getting 1.1 times 10 to the 3 Newton second. So therefore, the impulse of the water is this guy right here. So I got to be careful here. What is this impulse? Well, what this impulse tells us here is that I could say that in my lecture notes, I do the actual calculation for F average. In other words, we just calculated the impulse of the water, but if I use the mean value theorem, I can get the so-called average force of the water times the contact time. Now, the way I calculate the contact time is that I just say, what's the time that it takes him to go from a speed of, the square root of 2g y naught to rest? And that's how I calculate my contact time. And if you do that, here's what you find. You find that the average force of the water on Henry is 28,000 newtons. That's a lot, it turns out. That's 6,400 pounds of force. That is insane. Okay? That is insane. That's a lot of force. And I saw images of him where he was literally, I saw him on, what was it? It's in one of these old shows, like Tell the Truth or something like that. I don't remember quite the name of it. And I think he was like 74 when he did that jump off of like roughly 12 meters. And I'm telling you, I think when I saw that, I think I was in my early 20s. And I looked at, Henry's video and I'm thinking like, wow, this guy's like really old. He's going to really jump off this 12 meters. And I'm kind of like, my palms are a little bit, moist, going like, I wouldn't do that. There's no way in hell I would do that. But there's this guy in the 70s jumping off into that thing. And I'm going like, and then, eventually I says, I got to calculate this thing. And I get this 6,400 pounds. And I'm going like, there's no way. And the answer to the question really comes down to this, is that it's not the force that's the important thing. Henry feels the pressure. And the pressure is force divided by area. And if you compute that, what you find here is that the pressure on Henry as he hits the water is what is known as about a third of an atmosphere. And let me tell you, a third of an atmosphere is okay. You can handle a third of an atmosphere. But I was just like, I could not believe it. Another thing, just to keep moving along this thing here, is that if you jump from a high enough, height, water acts like concrete. Yeah. Because if if you jump into water, if you think about water, right? If you jump into water, one of the things here is that you typically come in at really slow speeds, right? So as you come in here, you jump into water with a slow speed. Now that's important because what that gives here is it gives the water molecules time to move. So therefore, you feel this really soft thing here. However, if your speed is too high, then water molecules cannot move away fast enough, and it is rigid. So at high enough speeds, dude, even though it's water, it's going to feel like concrete. Yeah, boy, I think that's freaking awesome when you think about that, right?